Yeah, thanks for joining us for what's probably the last session of the machine learning coffee seminar. And well, it's going to be a great conclusion for this season because we have here Mikko Koivisto, who's a full professor at the University of Helsinki, and he's going to tell us about probabilistic machine learning, specifically Bayesian inference of causal graphs, which sounds super interesting. So I'll leave you the mic.
Thank you. Thank you. Very nice to be here. Maybe somebody can close the door. There and so hello everyone here and everyone there over Zoom. Indeed, it's been a while since I last gave a talk in this seminar. I think it's some 6 years ago or so. And then the title was something like learning Bayesian networks or graphical models. Very similar business, actually. And indeed, I've been working on this topic now for two decades, 20 years. And still it's alive and kicking. So, this is something what is quite interesting here to me has always been it's a mix of two things. One is really the foundations of AI or machine learning. Think of it like the foundations of Bayesian inference, that sort of thing. Like in bit like the philosophical aspects of that. And the other part of is then algorithms, which is really where my own expertise is, and all my research papers mostly are about algorithms, fast computation of something. Like these two things I've always trying to combine. Now this is about, in a way again about the same graph. About the same topic about this causal graph, sometimes called Bayesian networks, a little bit depending on what the interpretation is. If the interpretation is causal, then we talk about causal graphs. And here I've been working on this. Other groups we were working on this topic for a long time. So we are already somewhere. But still, I think it's easy to identify things we have not yet been able to fully solve. So I will, in my talk, also touch a little bit about those topics. All right, so here is my plan. So I don't really have many slides. I could give this talk in 10 minutes or in 1 hour, or this is not something in between, maybe half an hour. That's my more or less the plan. I'll start with the causality. I'm here taking a particular approach to causality, namely Pearl's graph-based approach. And then we proceed to learning, and then again taking a particular paradigm, namely the Bayesian paradigm for statistical inference. And then finally, where I'll most likely will spend most of my time is about computation. That's gonna be the challenge, and there I'll mention some tricks, give an example of a sort of research I've been recently working to give some flavor, a little bit more technical content also to this representation. So covering quite a big thing in total, but of course not going deep, very deep in many places. All right, so now this is the starting point. When we talk about causal models, they look, following this Pearl's approach, they look something like this. And now I'd like to, okay, here it's easy to ask, like, how many of you have seen an object like this before? Okay, quite many of you. That's great, because then I don't need to explain everything in that much detail here. So very good. So we have some random variables here collected by a directed acyclic graph. That's the causal graph. And here what are the key things here are that for every variable here, it's a function of some other variables, namely the so-called parents maybe look at the incoming arcs here. Plus there is some the random variable that we take as some like a noise, or put some stochasticity there. So but otherwise this f is a fully deterministic function, and all randomness is due to this random variable u. So now of course this is now because the idea is that these are random variables, so they may take different values, but still we keep this graph fixed, and also these functions we keep fixed. So this is like we have the same causal, that's the basic assumption here, that we have the same causal structure of the model, and also the mechanisms are the same over different situations, even though random variables take different values. Okay. Now this entire model could be completely deterministic also. So that it could be that it's just that this u variable has no effect at all there. It's just fully deterministic. And then it becomes interesting if we indeed allow here something. Now this is just a mathematical model. It could be, I'm not yet saying what's the interpretation of this model. And then now it a little bit depends what your interpretation probability is already. If you think this is now a random variable, okay, this is like a stochastic function. Now if what I'm going to take later is that it could be that this is that the whole system is deterministic. There's like no true randomness anywhere. The old randomness is because we don't know something. So this, if you could think that this u is something that is just, we don't know everything. So there are some unknown factors. And because we don't know, we model it as a random sign. It's like a subjective Bayesian probability approach. That's one possibility. Not everybody is taking that approach. It's just a mathematical model. That's one way to interpret. You don't need to fix it that. And at the end, I'm also interested in computational challenges, algorithms, and it does not really matter there what the interpretation is when we are at that. All right, then maybe that's all I need to say at this point. So indeed, I'll call these direct causes, or the variables there, the parents of the respective guy here. So x1 and x3 are the parents of x4, but x2 is not. It may have some causal effect to x4, it's x2 also, but it's not a direct cause. Now, if you know the term intervention, means that we could set somehow. We set some value, let's say this x3 variable. Then it means that we sort of cut this connection from the parents. They don't affect anything if I can just set the value of x3. Sure. But otherwise the model is still would be the same. Okay, let's then proceed to the idea. Okay, we want to learn these models from data. Yes. So when we want to learn these models, maybe we want to learn both the structure and then the mechanisms. Now, a little bit depends on what sort of data we have, whether this is somehow easier or harder, this problem. Now, in an ideal case, we would be able to make some interventions or experiments, so to speak. One golden standard is randomized experiments. What people do in like a health sciences or something. Let's say there are control group and treatment group, like this. I'm sure you have heard of that before. So then, yes, that's sometimes possible, and maybe then we could be at that. We have such rich data. Another thing is that if you think of the system we had in the previous slide, but is it do we observe all the variables? Do we have data for all of them? Maybe in reality, maybe not. In a way that, okay, so what are the relevant variables? This could be discussed. What is relevant, or maybe something that is really playing a role in the graph. Is in the graph. So if we can observe everything, then maybe here, and yes, this is everything is maybe somehow easier and cleaner. But that's this is just how I'm a theory guy. I'm not doing any really applied data analysis or anything. So this is how please correct me if you know better, but this is how I see that more or less somehow the situation varies across different disciplines and sciences. Somehow in physics or chemistry, yes, maybe we can tell what are that these are the variables we need to measure. We can measure them. Maybe okay, we get the experiments. There are no like ethical. Maybe there are something could be expensive or difficult to really implement. Okay, so maybe not everything is possible, but still, when we proceed to this and the social sciences or some, well, human beings are involved, it's not that easy to somehow do some randomized experiments. Or let's say if you study how, let's say, education is a cause of something. Can you really set somebody's education for something? Well, no, you can't maybe force that. That would be somehow unethical. Just as an example, so that may be easily happens at this and here, and also that we can think. At least to me, it's easy to think that it's not that clear that we, in the first place, observe some of the relevant variables that are in the system. Maybe most of the variables that are really playing some key role are not in our data set. Now for this talk, and saying that somehow that here it should help if we have rich data and observe everything. Yes, that would be nice. Maybe even 2 uses, but it's not like interesting as a research from my point of view. Then again, I have to say that so far, where I've been working on is that we have been assume that we can observe the relevant variables. I'll get back to that. But on the other hand, I've been working in cases or settings where we don't assume we can do any experiments or interventions. So we have just so-called passively observed data. No interventions, no experimental data. And then the question is whether still it's possible to learn causal. So the task, indeed, what this talk is about is this. We want to discover the structural causal model, or let's say at least the underlying direct acyclic graph. Well, you can forget the mechanisms, those functions for a moment. Just think about the graph. We have given passively observed finite data. Okay, finite. So this is not going to be like an asymptotic, but what will happen if you have limited somehow in the limit, like any like such like that sort of theory results. Now, the key assumption is that we have given a promise that there are no hidden variables, sometimes called latent variables. We have measured everything. So this is quite a radical assumption, but this is then again something people have to do this assumption just because it makes things easier to handle like computation from the modeling perspective, even though we know that it's not quite true. This is something definitely we'd like to extend and generalize these methods. For these talks, still we've been working on that assumption. Now, if you think of now this tag, what is known that now it then depends whether you know a little bit about the theory of such causal graphical models or Bayesian networks, probabilistic graphical models. They infer conditional independencies among the random variables there, modeled by the graph. Conditional independencies. Now, if the learning only relies on that, like learning conditional independencies, we know that the best we can learn that maybe not, okay, maybe you can think that even if we have unlimited amounts of data, we can only discover what is called the Markov equivalence class. And that means, like to put it in simply, what was the Markov equivalence class? Let me give an example. Just that we have two variables, x, okay, maybe x1 and x2. So we have three possible graphs here. Empty graph, and then one edge like this, and then the reverse one. Those three graphs. Now, the two possible directions for these edges, those are equivalent in the sense that they are called Markov equivalent. They encode the same conditional independencies. But well, basically telling that these two variables are dependent. And that's not possible to, like, that simple direction is not possible to distinguish, learn from data. Like, is it this or that? Like, this fundamental. Of course, it would be nice to say whether x1 is causing x2 or the other way around. But that's only if our learning is based on conditional independencies only. If we assume more, something about the possible mechanisms underlying, then in fact we can learn the direction. It's possible to identify the direction. Now it depends what the assumptions are. But for example, in the model, if you remember this f function, if it's a linear function, and then sort of the noise term u is additive, and then that it's not Gaussian, non-Gaussian, so a linear additive model with a non-Gaussian noise or error, then it's possible. That's an example where it's possible to, well, that's, of course, that's a quite strong assumption. If you limit everything, if you're working on that assumption, and what if it's not somehow not or what if it's not a good model of reality, then that's something maybe you need to get back and think about this. But this is actually it looks like this is a bit open, like a research direction where not everything is yet known here or done here. It could be explored more, but it's not really the topic of this talk now. So I don't go there now, but telling that even though this Markov equivalence business leaves us with some pessimistic view, then again here this idea of putting some more assumptions, we are meaning, you know, inductive bias. That's what we always do in machine learning. We need to introduce some inductive bias to be able to learn anything. So assuming more, we can learn more in a way. So that leaves us with an optimistic view of this, that yes, it is actually possible. So this framework so far so good. All right, then Bayes was mentioned, but now we really look at it in more concrete terms, what it means here. So if we're going to follow the Bayesian approach, then what learning means now? Learning that graph G from data G, it's the same as representing somehow the posterior distribution, the posterior distribution of the graphs. So if we can have some representation of that, then we can say we have learned. We have learned from data, right? Well, that's actually probably no. Okay, it's proportional with its prior, and then the likelihood. Even though here it's often called the marginal likelihood, because the mechanisms, like the parameterized functions, we integrate away. So it's like marginal likelihood. All right, so, and this is one motivation here is that having the entire distribution, we are able to represent uncertainty, what is left after learning, like how much we really have learned. Compare that to, let's say that we just take the mode, we maximize the posterior. Well, there are in this business, many research groups have many papers study the maximization optimization problem. They learn one model and that's it. One fixed graph maybe with fixed parameters. So that would be maybe one possibility here. But if you think about this probability of that, even if it's the best graph, best model, the probability can be very small. High dimension. Okay, here it's not that small compared to everything else. Here the mass, but you can imagine a high dimensional space. It's going to be ridiculously small. So somehow, the point is maybe it's not that wise to somehow just pick that and then pretend that okay, now I have learned the thing and somehow ignore everything else. So we want to basically keep it. Okay, easier said than done. But what helps us here, we commonly almost always make some structural assumptions when we do this modeling. I'm not going to go deeper than that here. But commonly what we do is do things that are assumptions that imply what is called decomposability of the marginal likelihood term. So that the marginal likelihood decomposes into a product over the variables. We have some number of variables, n variables, those nodes in the graph. And then we have for each, we have some term. The respective data is the column in your data matrix, given the values for the parent variables in the data matrix. And well, here, if it's this depends on the graph, so we have to somewhere here also tell the but here the point actually we don't even need to tell the entire graph here, but just that it has these parents. That variable has these parents. We don't even need to tell what like the global graph here. All right, so we have this sort of like a global thing decomposes into local components. And this is oftentimes helpful. It's helpful from the modeling perspective, like given some priors and so how to express those things, but also then computationally, having such structure. Now it already looks at somehow possible to be able to somehow make sense to somehow even try to do something for the high dimensional posterior distribution. All right. Now okay, then there are some interesting things. I already mentioned these mechanisms. We don't see those mechanisms here in this formula, but they are unknown to us what they are. So okay, parameterized functions we don't know what they are, and in here for each we have integrated already away. Imagine that these are integrals already of where we have integrated away these mechanisms with respect to some priors we introduced. And there we have what is not explicit here is that to be able to get this product form, it means the prior we have for those mechanisms has this product structure also. But like you think that we have the nature has drawn these functions from some distribution independently for each variable from the prior, if you think it as a generative model. Then because they are independent, we can this big integral collapses in the product of small local integrals. And okay, those integrals, why I don't show any integrals here is that in practice we use such nice models here that we have closed form solutions. Closed form solutions. Whether some linear Gaussian model or some big multinomial tables, conditional probability tables, like a full parameterized discrete models. And things are actually quite easy, that part. All right. So yeah, let's see. Time is running. So then this is Okay, maybe a few words about this. Usually in this Bayesian approach, with this linear Gaussian model or those discrete big tables, we typically use some very special primers, so that the all DAGs that are Markov equivalent get the same probability at the end. That's what we oftentimes do. You remember what Markov equivalence means. So, but indeed, we need to use quite special priors, and as soon as we don't use special, if we do something a little bit different, then already different DAGs in the same Markov equivalence class. Think about this two variable case. They actually get different probabilities. But this is not that easy really, because there are results of even then asymptotically. If you get more and more data, they get like the probabilities will approach the same value again. So it had to be. This is like a subtle issue then how to set what priors to put so that you can really learn causal direction here. So I'm here today. I'm not proceeding to that, but just want to raise this point again. Okay, let's proceed to computation. Okay, some good news. It's possible to, okay, let's think about it. We have this posterior distribution. We want to represent the posterior. We want to represent the posterior, but that's not like always want to really like somehow represent the full distribution. Oftentimes it's okay if we can compute some expectations, expected values. Let's say the probability of some event is already an expectation of the indicator function of that event, right? So like we can exactly compute, even though the space of DAGs is quite large. It grows very rapidly in the number of variables, up to somewhat 25 variables. It's quite okay. These are non-trivial algorithms, exponential time algorithms. If you have 100 variables, these algorithms don't scale. You can't do it. But up to 25, it's still, yeah, you can do it. So if you do some applied work and in your data set, you have some 20 variables, then yes, there are exact algorithms that can solve it, your problem. There's no need to do something approximate or something. Or if sometimes here still, okay, it's certain form of expectations are doable here, but if your case is not, still it's possible to exactly sample from the posterior distribution using certain methods. The most recent will be presented in the next UAI conference within 2 months. Our paper got just very recently accepted about this topic. But then if you have more variables, then we need to resort to something else. And the usual technique here is Markov chain multiple. You have MC. That's certainly something you've heard before. Now, there's been a series of developments over the past 3 decades. Now, these methods, we don't unfortunately have any accuracy guarantees. Like oftentimes in practice, when you do some Bayesian statistics or something, you run MC, you don't really have any accuracy guarantees. But still, also this gets now that after all these developments, I could say that they work usually pretty well in practice. This is a vague statement, but up to some hundreds of variables, you can be quite optimistic that in your case, everything will do a good job, even though we can't guarantee. And there are data sets and cases where we can see that there are big challenges that it's not, our methods are not quite good enough in some cases. So and we still do research here. Now all here is that we keep the assumption that there's no hidden variables. if we add that, then we don't have actual methods. I think in the next ICML conference, there seems to be one paper that gives a score-based approach to learn Bayesian networks or causal graphs with hidden variables. So I'm curious to see what that is. All right. Here are some developments. I mentioned, maybe I just want to quickly mention some points here. Now, if you want to sample your Markov chain multi-column method, what is the state space? Well, quite natural state space is the space of graphs, right? DAGs. And then you do some simple operations. You add an edge, you leave an edge, or reverse the direction of edge. This is how you random walk in the space of DAGs. Now, that's an old stuff. Then there are other developments, and one observation is that if instead your state space is a linear ordering of the nodes, the variables, it's like n factorial. This is the number of possibilities of permutation. Then for each of them, already it's like it covers an exponential number of DAGs. So you're able to somehow collapse the state space into a smaller state space and get, well, better results as they shown in their paper. They also introduce some other good ideas there in their paper. Then there are, okay, you could go to the partial orders like we did a few years ago, not like a linear orders, but so like a bucket orders where you can cover with one such order, you can cover even more DAGs by one state. And again, your posterior distribution or landscape gets smoother and nicer. But here, one issue here is that actually introduces the bias, an unwanted bias, because that's because if you think about one DAG, one graph, that's actually compatible with not just one linear order, but many. So in this way, you are easily favoring DAGs that are compatible with many linear orders. Now there is a paper like try to remove this bias. Well, with some success, could be discussed whether it really solves the issue, but at least is aware of that issue. But then what really solves the issue is when we go to something similar than linear orders, but what we call root partitions. And that's what we've been working recently, this root partition. There are also some reasons using quite different methods of using variational inference within this MCM's Bayesian framework. I'm not going to go there, but I'll tell a little bit some more technical stuff what is root partitions, because I still have a few minutes time. So here you see an example of a root partition. So we partition our vertices into some number of parts, sets of vertices or variables, if you like. Okay, so we have here one DAG, one graph. The point is that for that, this root partition is a unique thing. So that's why we don't introduce any bias, because the root for any DAG is a unique thing. It's root partition. So we get it. So we pick the root nodes here, like sources, the DAG. That's the first part, and we remove and then repeat the next sources. We get the second part, and so on continue. That's how we get this partition. Now, because we want our random walk will be in this space of these sort of partitions. We want to have a random walk over these. We want to, from one root partition, go to some neighboring root partition. So how to do that? Well, we propose something using Metropolis Hastings algorithm. You may have heard if you know CMC stuff. And so, and for to do that, and we need to be able to score, give that basically the posterior, what's the posterior probability of the root partition. So, well, we get that by summing the scores of posterior probabilities of the DAGs that are compatible with that. Now, that's a big summation of DAGs, which is in a way a good thing, because one state is able to cover lots of DAGs. already, but computationally, it is a bit challenged. The good news is that, again, we have a nice decomposition in the product. So for each node, we have its own term here. If you look at this term, well, for each, we have one term, one by one. We have this big product here, or relatively big product. And then we have some score for that guy. Now it depends on we need to know what is the previous part, and then the union of all preceding parts. Those two things we need to know, because what that thing is we need to compute a rather big summation of all possibilities for the parent sets. Now this is the set of parent sets, as here is an example one. And we need to go through each and every possibility. And that can potentially be large. The all possibilities we could imagine from these sets, like a subsets of some possible sets. Okay, there's some constraint. We need to pick at least one from this. It comes from the definition here. So the question is computationally, and that's where I've been working recently, is how to efficiently compute this sum, or how to sample correspondingly. So if you think of this as like a partition function, like proportional to these scores, we want to sample one set according to these weights, these scores, right? So the brute force would be that you just do it, but because it's a bit potentially a big summation, you don't really want to. You'd like to do something more clever. So now if you think, okay, this is one context where we have big summation, but of course, if you do some probabilistic machine learning, in particular Bayesian machine learning, I think this is something that you may encounter in different contexts, like a similar thing, big summation. You would like to get that, how to do that. So contact me. So I may have some ideas. This is my business. Yeah. So this is already an old idea, but now if you think what we can do, we have a big list of parent sets, possible parent sets. We sort based on these scores. So that we have the high scores in the top. We start from those, and then so we sort in decreasing order. Okay, then we need to, at any point, know how much left is below that, because we want to do this in an approximate way, so that we have controlled approximation of this summation. So this is now already the sampling part, but the first part actually does the summation up to some error, like small error. We can set some. So as simply we start accumulating the scores, starting from the largest ones. Well, we need to check that the constraint, if it's really included in the summation. We check if it is, then we update the sum. All right, now we have done the summation. Now we got the sampling uniform random variable between the 0 and this approximate sum, which is only slightly smaller than what the real total is. And then again did the same and just cut, but once we have reached. Okay, so this is like the first part. This is an old stuff already. Now what we've been recently thinking of like improving this. It's not like you should think that this is not like one example of my research, one more technical. This is not like all research covering what I've been thinking, but it's an example of what flavor of research. So this is the question: can we safely throw away some possible parent sets from the list? That's pre-processing. So that we only much shorter list, somehow safely, if they have a very small score. Now we should compare this to a case where suppose we are not summing anything. We are interested in the maximization problem, finding the best, like highest scoring graph. Suppose, like for the moment. Then it's easy to see that we could prune a set, like throw it away, if it has a subset that has better score. Because you could always replace your parent set by its subset. If it's better score, you only get the better score, and you would not create any directed cycles. So you don't violate the acyclicity constraint. So So but this is what we can, so this is like a inspiring, like how you try to do something similar in flavor. And now this is what we can do. I'm not gonna read this through, but the point is that we do something that we can prove a theory about. We can guarantee some, okay, epsilon safer, because here we need to, here is no approximation. Here we do summation or sampling, we need there's some approximation. So the relative error for summing and sampling is bounded by epsilon. Of what the total variation distance, if you think about sampling part. And then we have some rule. We prune a set, we throw it away if certain criteria. And then we do it. The point is, okay, so we have a theorem telling that it's safe. It works. We know how much the error is, so we can control that. But of course, empirical, the question is, does it really prove anything? If it can be, do we get any saving? And here's some empirical results for this is that these are now cases that how many sets are left? 6%, and here we already see a thick, like almost everything we can throw away without, but still we have the guarantees that for any summation query that we will be asked, we will get an approximate or controlled approximate risk. Okay, time is running. I spent quite a lot of time here, so I move to conclusions now. And Bayesian first nice answer that is fully taken into account. Okay, the identifiability thing is an interesting thing. I didn't talk about that very much today. Scalable MCMC, we can do quite a lot. We still are working on that. But yes, no accuracy guarantees there. And the big thing is that still we don't allow hidden variables at the moment. So that's the natural thing where we should go next. Right. That's all. Thanks.
Do you have any question here on Zoom?
Yeah, one question. Thank you for the talk. So, how do you put priors on the causal graphs?
Yeah. Okay. Yeah. I said I'm a theory guy. So for me, like any prior is okay. Like if you think, then I just run to computation. So, but then it depends what your prior is. You think like a uniform prior over all graphs. So all possible graphs are equally probable. That's one possibility. It's like from the equations you think basically you just ignore the prior part. You just have the marginal likelihood because the rest of it is a uniform, the same constant for everything. So that's already something that people even use them. Even though that's not a very good prior, I think good in some sense, because then you actually give almost all prior probability mass to graphs that are very dense, like half of the edges are there. And that's maybe, well, the idea in these models, causal graphs, Bayesian networks, typically is that the graph is something sparse. That's kind of the idea. So there are other, you put some value for each edge, like and then you take a product of that, some point not natural for graphs. You want to have it sound like a product structure. That's the essential thing from to then to be able to do this computation side advertise.
Thanks.
I have naive question, a very naive question. It's about the theoretical culture graph. Have you ever heard about that idea? Because, like, for example, if you have EU slide, you said that you can detect the culture graph is at around 25 hours long. But if you have more, then you think those theoretical methods can be something like that?
Theoretical.
Yeah.
Theoretical. That I'm not familiar enough with that. So I would guess that it's probably not. We are not then able to compute up to 25. I would guess so, but I can't recall now exactly how we define hierarchical. What's the definition of that in this case? But if the hierarchical means that your prior, or let's say causal mechanisms or local models, they are not independent, but you have some hierarchy, that they are somehow similar to each other. That's typically what you have in hierarchical models, that you have some, can you use the same prior? You say that your objects are similar to each other in some way. You don't know exactly in what way, but in some way, you have some hyperpriors there, but that then destroys this decomposability assumption we use here.
Okay.
So yeah, but maybe if you can somehow there's some auto. Yeah, I don't know.
Let me assume, sorry, but let me assume a case. For example, we have a space graph and we have several systems that interact with each other. We have some causal graph, or we have some causalities between those systems. And inside each system, we have several different sensors, and we also have that causal interactions between those sensors. So if I so last year I read a paper, but sorry, I didn't find that yet. This is that we can build a system which consists of several subgraphs, consider of that together. So here we can have the higher higher rank, we can have the causality belong different systems, and inside the system we can have that using sense.
Yeah, certainly I think it makes sense, and there are, yeah, I can easily think of some like hierarchical models, and so in a way the model we started with this graph, this structural graph, causal graph model is somehow like a flat model compared to many. I don't know what kind of data you have in that. If you really assume we have something, it's like a big table, like that. There's no other much more structure. There's no time series, no like any indeed like hierarchical structure. But in some other cases, it could be that it's more complicated the setting, and you need to add up and see whether these add up to such cases with these methods.
Yeah, thank you. Maybe we can talk later.
Yeah. Okay.
All right, thanks again.
Right. And